Hi, this is Andy from Yahoo. I would like to share some of our listener work. I tried to do the machine learning on the Hadoop clusters. And since the audience is really small, so let's try to be interactive, otherwise it's going to be boring. So what I would like to do is share some of the use cases in which that we are doing machine learning stuff, and then talk about the challenge we face at Yahoo. I try to do the machine learning, and then we will talk about our solutions and some of the accomplishment we were able to achieve. I think my desire is just make you think, sounds like lots of low-hanging fruits there with your data. Let's do something with it, right? So okay, so let's talk about the use case. I think one of my first favorite use case is our photo service called Flickr. So as many of you, take all the pictures, put online, then want to looking for them, right? Then the question, at Yahoo we have a service called Flickr. Have several billion, photos in it. And as a user, when you upload the pictures, you do not really give a tag kind of thing, right? It's so easy to take pictures. Why do you want to waste time, give a tag? But on the one hand, once you have the picture over there, you're still looking for it. And so instead of having to ask our user to give us the tag, we say, our computer should do the work. Right? Then so then the thing you wanted to do is be able to search for all the different things, based on things, based on objects, based on people, all those things in the picture. So I think the challenge is to see how you do that thing, right? And then to learn the content in your picture is a very known problem for the deep learning community or for the vision research areas. So for us, it's a real business problem because if we do not provide an accurate prediction about what's inside the picture, our user will have a harder time. Then they just not come back to looking at pictures, or just easily jump into another photo service to do their job. So this is one of our applications. So then second, so as you know, like Yahoo, traditionally, the search and advertisement is one of our key areas. So as a user, when you come to our site, when you're looking for the things, we need to understand what your intention is. Based on that intentions, we give you the list of the search result page. On the other hand, we also, also the ordering, how those get ranked is based on, how close those content is. Again, this is nothing but is apply some machine learning algorithm to do the job. Along our search result page, we put a few ads on it. And the intention of those ads is to try to give you the product very close to whatever you are looking for, right? And again, it's a problem about the machine learning, try to match your query and the ads. And then from our point of view, we also try to make sure the ads we give to you have the high likelihood that you want to take an action. So the ads prediction is a well-known problem for the machine learning community for them. So now let's say talk about the advertisement in general. So there's many cases, right? When you come to our search site, we try to give you the ads. Later on, when you go to some other place, based on whatever you searched before, we try to do the targeting again, right? And then even you come to our mail page, we try to give you something that ads that's relevant to your experience. So over there, traditionally, what you try to do is based on the keyword, right? So based on the keyword you give them to us before in your search time, then we try to find this stuff. So the challenge for many of one of the challenges we have is if we just look at exactly the search term you give to us before, the number of ads we could find. Oh, seems to be very sensitive. Okay, so the challenge over there is if you just do the exact syntactical matching, you could not find enough ads. So as a result, there are the lost opportunities from the company point of view. So instead, what we wanted to do is extend the search keywords beyond the syntactical matchings and go toward the semantic matchings. So let's say that the search term, then we want to find the semantically very similar other term. If those terms have some ads you could find matching for it, then we will give it the ads. Because from the user point of view, it really does not matter whether you do syntactic or semantic. Actually, it will be ideal you do the semantic matching, right? So also are just examples of the machine learning, right? And then from our point of view, to us, the main challenge at Yahoo is the skills. So first of all, we have, there's so much data you have at hand, and then how you learn from those data, right? Then until maybe 34 years ago, we have been using very simple algorithms. As a result, it takes actually a few weeks to come up with models. On the other hand, if you think about the reality, your real world, changes so much. If a few weeks later you come up with a model, that's not be much, right? So what you really want is that really reduce the latencies from the starting of your learning time and your model as a result of your models. Then the second is, as we noticed that many of our data scientists, after they got a PhDs, we had a significant amount of data scientists. They spend, after if you look into our data scientists, they spend a significant amount of time to do what we call the feature engineering. And what they need to try to do is, among all those, billions of the feature you could potentially look, they try to do all those imagination things, do the analysis, try to nail down them to a small number of features. And so you're doing lots of data, manipulation, try to apply some heuristics, and try to map the raw data into some manageable number of the features so that they could apply some machine learning algorithms. And then on the other hand, it's not just a one single algorithm we could have. There's many algorithms we needed to have. So thinking along all those lines, the question is, as a company, how do you come up with a set of the machine learning algorithms that achieve your business goals and then make your data scientists efficient? So that has been the charter for my team. So we have been trying to say, in the public, there are many well-defined basic machine learning algorithms in the marketplace, but they are not good enough for us. So we wanted to have some machine learning algorithms that will be able to help us to address those scalability challenges. We enable our data scientists not to spend so much time to look at the data, to try to squeeze down to a small number of features. Do not want them to wait for many days to see the result of their experimentations. And then, provide a good number of the machine learning algorithms, enable them, just quickly do the iteration of the experiment as a result, achieve the business goal they try to address. So, before I talk to you, share with you some of the examples. Honestly, this is not a problem just Yahoo has. And if you know that in the deep learning community, there was one of the famous things for the image classification, right? And So the question, I think, that was essentially that they give you a set of the pictures. Wanted the system to identify what's the category, what's the inside in the pictures. There was about 1,000 category in it, and so the major breakthrough happened was just a few years, 34 years back, and our friend in the Google side, they won the competition. So that was essentially was a starting point. Made the deep learning really popular in the industry. And then so that was why the deep learning now is a buzzword everywhere. And on the other hand, if you look deeper into it, like what they have is it actually requires significant resource to learn their models. When they came up with that models, they're actually using a large clusters. This solution called the disk brief solutions that Jeff Dean's team came up, and that are using many thousands of CPUs. And then later on, that's why as a result, they start looking into the new generation of the deep learning framework. Now the one I think you may have heard about is called TensorFlow. And then further on, right? Then they look like look at the CPU is too slow. Then look into the GPUs, and from the GPU sounds like it's still there's some challenges. Then Google guys actually decided to develop their own chip called the Tensor Processing Units (TPUs), right? And so obviously this is just one example that in order to achieve those fast good result for your machine learning, deep learning, you need to have a significant computation resource to look into a massive amount of data. So at Yahoo, we are not lucky enough as be able to spend all the money like Google guys could spend. So we thought we have a secret weapons, that's our Hadoop cluster. So as you guys know, Yahoo has been working on the Hadoop for many years. So as a result, we have all of our data about our user, about our product, actually is sitting in our Hadoop cluster. So we have also data over there. And then the second is we do have a few thousand machines sitting in those Hadoop clusters. So then our desire was, at that point was, why don't we create a machine learning solutions in that environment? So that is essentially this our. So that was the direction we decided to take about 3 years back, and we made some good progress on it. I think I mentioned some of those progress at the last two Hadoop summit here. Among them, as we mentioned, we reported to the community that we extended our Hadoop clusters to have GPU machines in addition to the CPU machines. And then our GPU machines, has some advanced network between them called the InfiniBand. So that because part of the reason is when you do the machine learning, deep learning, there's a lot of data you need to communicate between all machines. Then the bandwidth of the machines means a lot when you consider how long does it take to finish your training job. And from the software point of view, on the other hand, where we have developed some infrastructure softwares like parameter servers, and then on top of our Hadoop Spark clusters, we have developed half a dozen or so algorithms, I would call them the classic machine learning algorithm type of things. And then we also have been working on the deep learning in the last several years. So in the next few slides, I wanted to just share with you some of the fun stuff we did in those machine learning algorithms. So the first one I want to talk with you is a system called word to vect or word embedding algorithm. That one we gave a technical talk at the CIKM conference last year. And I want to mention that because it demonstrates how much values you could gain by doing the innovation in the machine learning algorithm and with big data. And then second one I want to also mention is decision tree algorithms. That one was we published at the NIPS conference last year. It demonstrated the importance to do the collaboration with your friends in the universities. And last but not least, I want to share some of our work on the deep learnings. And actually that will be shortly, why we need to do the open source, why we, as an industry, work together will be stronger than just competing with each other, right? So, word to vect. I do not know how many of you know word to vect. Anybody know? Okay. So, word to vect was so basically try to do is try to come up with the semantic representations of your word instead of its syntactical meanings, right? So what you want is learn from some Wikipedia or whatever let's say your favorite language, right? Learn from those documents, then you try to learn the semantics of each individual word, and then represent those semantics by a vector of numbers, of float point, whatever, right? So let's say you have the Paris, you have have a few hundred numbers along those. All those words you have, you just become numbers at the end. So then the word to vector, what to give you is when you look into those vectors, it actually gives you a good understandings. For the set of the words that are very close by, you will see that in that vector space they are very nearby. Then on top of it, you could apply certain mathematical manipulations against that vectors, right? So then what we wanted to do is say, let's imagine you have those things for your query, right? Let's say you have those vectors for your ads. Then, if you could have those, then the Yahoo's business of this, try to find ads against your search term. Essentially, it's become a word to vector applications. In other words, let's say you have a query in this, one vector here, right? Then imagine all those, what you need looking for is all those ads in, nearby in that vector space. Because that means they are very similar to what the user is looking for. And all those ads that's far away from that query term, that are just useless. Just, bogus ads. From the user point of view, they will hate it. Right? So then the question now you're going to say, okay, now so how are you going to learn the vector of the ads or queries? So luckily, by looking into what our user did at our site, we actually have enough learning data. So more specifically, what we are saying here is treat all the user sessions as a single sentence. So you come to Yahoo site, spend 30 minutes on it. Let's say you're looking for some search term, gas cap replacement for a car. That's your first search term, right? And then after you type that thing, you find some, we give you a page with some link on it. You click some link. Then later on, this link is useless. I type another search term, gas door replacement for a car. Then you click another link. This is still not good. You type another set of the terms. You look at some ads. So you cheat that thing. That's essentially what you did from our point of view during that single session.
So we consider that a sentence. Consider that a Yahoo language sentence. Okay. Now so then you imagine, so, if you would have the basic word-to-vector algorithms, rather than just apply here, right? Then even so, the only difference between all sentence versus the traditional English sentence is we just have many, many more vocabularies, right? Then the challenge though is many of the word-to-vector algorithm available in the marketplace just could only deal with a small number of the vocabularies. Like the one from Google could deal with maybe, small number for millions of words. Because English words just have so many, right? What's the point, Then when we try to apply that thing to all applications, then we need a few hundreds, easily hundreds, millions of words, vocabulary we need to handle. Because the more you could handle, that means more possibilities we have to give a user a relevant ads. So again, so what we decided to do is so the team we took on, okay, we're going to come up a word-to-vector algorithm, be able to handle 200 million vocabularies, and be able to use in certain a standard set of the commodity hardware to be able to do the job, and then be able to address all of the limitations that in the public machine learning algorithm has. So anyway, so we have been working on it, and I do not want to walk us through the details. So end of the day is that we have parameter servers, and we came up with an algorithm that is really optimized for distributed learnings. I think at this point, it could very easily competing with any other machine learning or word-to-vector implementation in the industry, right? And so we do all those the parameter server we developed is not as dumb like it's key value pair stores. It has the design pattern we learned from Hadoop MapReduce in it. So you could easily send some operations here, for example, as I was charting here, sending some operation to our parameter servers. So as a result, we could leverage, make all the machine, all the resource optimum, well utilized. So okay, so what's the result, right? So this is the result we published last year. So at the beginning, we tried a single machine word-to-vector series. So it was good, achieved some, good improvement over our traditional matching algorithms, that's syntactical matching, right? And with our distributed word-to-vector algorithm, we achieved 10% revenue improvement per search. That's a single algorithm. If you think about, for the people who, you are familiar with Yahoo, right? We have so many data scientists, so many engineers working on this particular problems for so many years. This is just unimaginable when at the beginning we saw the result. I think it just demonstrates how much value you could have looking into your data. Okay, I thought this was a fun thing to demonstrate as a technologist for working on the big data, how much difference you could make. So then the second I want to just mention, for another algorithm called the decision tree, right? I think the word-to-vector might be not so well known. Decision tree, everybody knows it, right? So if you think about the decision trees, so there was given any problems, you just essentially, you divide your thing up based on certain criteria. At the end, you say, okay, based on those things, I know what this thing is, right? So now the question though is how are you going to do a large, if you have lots of data, lots of machines, how are you going to do the distributed decision tree? So our friend in Google, for example, came up with this called solutions. Basically say, let's divide the training examples by machines. So let's say you have 10 machines, each machine going to take 1/10 of the training examples. Then somehow they communicate with one another by master or something. And through that experience, you should be able to come up with a nice decision trees. Then we tried that with our search programs. It did not really work as it is in our environment. So we say, why don't we do a minor change? Instead of partition by the examples, why don't we partition by the features? Because what we wanted to do is be able to look at, many thousands of the features and come up optimal decision trees. And then the result is actually we published a joint paper with our friend from Stanford, MIT. And that was essentially the difference that we made. And we made the code open source available for the community. And right, so if you look into the algorithm, the diagram over there, that actually is indicating, how fast, if by do the innovation of the algorithm, how fast is this thing going to be. So the green color one is the algorithm, how much time must we spend in all algorithm versus the color is the blue, I guess. Blue is the tradition as the MLlib, and then the red one is a very popular XGBoost. Right? If you're looking in each case, whether it's the MNIST algorithms or with the Yahoo datasets, in both cases, you could see the difference is huge. And certainly beyond that, we apply this thing to our, for example, our search. When we decide to say what kind of result page we give to you, we actually, among them, one of the algorithms we applied is the gradient boost decision trees. Again, over there, we logically apply the same ideas in our algorithms. And because we were able to leverage all the machines that optimize, do this through the optimizations of the algorithms, we were able to achieve 30x speed up. So that was why early on we said, the early days we spent several weeks to do the trainings. Now within a single day, we will be able to produce new models. Then let me also mention the deep learning thing, right? So deep learning, is very popular. It's trying to simulate how our brains, how a human being learns all those things by a thing called neural network. So as I mentioned as the early examples, like to do the deep learning actually taking much more computation resource than classic machine learning. So as a result, we thought, we needed to do all the innovation on it so that we could, boost up the adoption of the deep learning, especially for the users who has a lot of data. So that's why we, if you guys might have heard about it, like in the last 2 years, Yahoo released 2 frameworks. One is called the CaffeOnSpark. That essentially was that brought the deep learning framework called Caffe from Berkeley into mass. Caffe is a very popular framework for the vision communities. Like our Flickr team, like all their data scientists essentially, using Caffe every day. And it's about how you be able to using Caffe and to learn the data you have in the HDFS, like in HDFS. And then we open sourced that code in February last year. And this year, about 1 year later, we released another thing called TensorFlowOnSpark. TensorFlow is a framework you guys must know from Google. But we try to make it easy for the big data community to use. And there's some testimony you could see from our friend from Microsoft and from Google. And so I just wanted to highlight some of the how you do the innovations in the thing like deep learning, right? So the idea really simple, right? So assuming you have all the machines, right? So why don't you, so the setting this is when we started the project, for example, the many framework, deep learning framework, were created by the mathematicians, essentially. So what they care, they know how to come up with more deep learning implementation for single machines. It's really hard for them to imagine, say, if I have 100 machines, what I'm going to do with it. So we thought, we are the system guy. We have worked on the distributed system for many, many years. So one simple way you could do is to make this so the Caffe framework or the Tensor framework to sit in each individual machines, right? And then somehow come up with the ways enable them to communicate with one another. For the deep learning, for the CaffeOnSpark, we decided to do using the MPI or RDMA. RDMA is a way to enable one GPU to access the memory of another GPU directly. So that's kind of very important. And then the result was when we compare with a single machine, GPU trainings, we will be able to achieve significant improvement. In the early on, for example, if you have one single GPU, when we try to do the job for the one use case, it will take up 39 hours to achieve even the 60% top 5 accuracy. And then, when we add more on it, if we're using 32 GPUs, we were able to achieve, much better result. Then similarly, when the Google guy released their TensorFlow things, if you know that when they released the TensorFlow early beginning, it's for single machines. Then then about 6 months later, they released the distributed TensorFlow. But what is that required though is you need to set up a cluster of TensorFlow servers. So you may have some cluster available for your big data things. You cannot use them. So we thought that's at least for Yahoo we cannot afford to ask our boss to spend or waste all this money. We thought why don't we apply the same design pattern we had for the CaffeOnSpark for the TensorFlow. So the result of what we achieve is I think we have achieved essentially the same scalability as the dedicated TensorFlow cluster. So that means you do not need to set up your dedicated TensorFlow cluster. As long as you have those machines available in your Yarn or whatever the resource manager you have in your Spark Hadoop clusters, you should be able to do the learnings. And then the solution we put for the TensorFlowOnSpark does not introduce any overhead for you. So anyways, for the details, I will encourage you to listen to the technical presentations we're going to give Tuesday and Wednesday. And Tuesday we will talk about the TensorFlowOnSpark. Wednesday we will give you the recent update of the CaffeOnSpark. So with that, I wanted to wrap up and ask questions and get some questions. Essentially, hopefully I convinced you machine learning, big data together could have a significant business impact. And for the technologist, hopefully you see the opportunities to do the innovations. Because like until 3 or 4 years back, for the people know me, I know nothing about machine learning, deep learning. But we made significant progress in the other areas. So with that, thanks for your attention, and see if you have any questions.
Thank you, Andy. So we'll take a few minutes if you have any questions before we move to the next speaker. Any questions? I can bring the mic down.
To become a data scientist, PhD is required. To become a data scientist, most of the companies looking for PhD people. Is it required?
I think that's the choice individual company need to make. For example, the thing I want to mention to you though is, for example, in my team, I have been very selective to have people in my team. And one of my top engineer, he joined my team with a bachelor's degree in physics and applied maths. That's it. Even not computer science. He's my top. He's my superstar.
Thank you.
I think it really depends on. I feel that there's a lot of low-hanging fruits over there. It depends on what your needs is. Likely, you will find some ways to make a difference. I mean, if you think about the things we did, like for TensorFlow, like when we open sourced our code, I think we open sourced on Monday. I think it was the second Monday of February this year. 2 days later, when Google guy had the TensorFlow Dev Summit, I went there on the stage. One of their top engineers was keep talking about how great Yahoo's TensorFlowOnSpark was. I think I did not pay anything. Then later on, after he came up the stage, then I said, where you came up with those things? He said, ever since you guys released it, we have been talking about it. So I said, can we work together? So I said, how about we work on it? How about I give away among all the pieces of the contribution we made? So we have this like Spark integration with the TensorFlow. And then the network layers, we have this RDMA things. I thought I do not want to keep this RDMA. I'm not a network guy, right? Then we give them the code. So they were super excited. Then I said, okay, let me go back. We will set up a test environment so that we could test your RDMA code. So after he gave me and we have a test environment now. Then we give them the code. Then they jumped in, merged the code within a single week. You will imagine, right? I mean, Google guy, they are the most, all the genius there, right? I have a small team. So that's why I think certainly with a PhD make the life easier. I have to admit I have a PhD, but I think there was no significant portion of my team do not have a PhDs. I think it's about your mindset. If you, as a leader of your organization, you need to find the ways to how to leverage those talents. Any other questions? Okay.
What was the driving motivation for InfiniBand over Ethernet? I'm curious. And ditto with RDMA versus just straight up TCP IP type stuff.
Yeah. So the question is why we decided to go to the InfiniBand, right? So as I mentioned earlier on, for the deep learning, there's significant the gradients needed to be exchanged for the distributed learning. And the gradient is significant for each iterations, you may need to exchange a few megabytes data between nodes. So then it depends on how deep your model is. So the amount of the time when we started the effort, we saw that our machine is not busy, but just
It's network.
network become a bottleneck.
Was it bandwidth or latency or both?
I think I was related to both. And then again, those things, that's what motivated us to look into those things. And then I think now you see, like, the many, and we certainly have some reference points, like, if our neighbors, you look at NASA, right? Those places, they have also the environment over there, we took a peek, then, So, sounds like it's an interesting technical problem to attack, then we can jump into it. Any other question? Thank you.